So we'll now start a new chapter. So this is differentiation. So one of the important features of differential and integral calculus is that they are differentiation and integration are really two sides of the same coin. More precisely, the fundamental theorem states that if you have f is a Riemann integrable function, which is the derivative of a function capital F, so f Riemann integrable, f equals capital F dash, then fb minus fa equals integral a to b f of x dx. So Riemann integral on ab, let's say. Okay, so we would like to investigate how far this goes. Well, so investigate how far this is true if f is differentiable only almost everywhere and f dash equal to f almost everywhere. So we want this, and we want to know if you can have the same result. So now let us consider the Cantor function. So f of 0 equals 0, f of 1 equal to 1, f is a monotonically increasing continuous function. Now if C is the Cantor set, then C complement is the disjoint union of intervals, if you remember the construction, and on each interval, on each such interval, if you remember the construction of the Cantor function, f is a constant, implies f dash equal to 0. Thus f is differentiable on C complement, that is C is of measure 0, it's almost everywhere, and f equal to 0 almost everywhere. But f dash, sorry, but int f of 1 minus f of 0 equals 1 minus 0, which is equal to 1, whereas integral on AB f dash dm1 equal to 0. So these two are not equal. So the fundamental theorem of calculus, one has to be a little careful when we want to do. So we want to investigate, so to investigate, to give conditions when we have fb minus fa equals integral a to b f dash dm1. So when can we write this? So we want to see, so we will start looking at various classes of differentiable functions which are differentiable almost everywhere. So the first class we want to see are monotonic functions. So we will, before we investigate monotonic functions, we are going to prove a very technical result. So definition: let I be a collection of intervals covering a set E of R. It is said to be a Vitali covering. Vitali is an Italian mathematician of E if for every epsilon positive and for every x in E there exists I interval in I such that x belongs to I and m1 of I is less than epsilon. So in other words, every point of E can be covered by an interval in this collection which is of arbitrarily small size. Okay, such Vitali coverings are very common when you are investigating local properties of functions, especially differentiability of functions, because what you do when you differentiate, you look at the function in the neighborhood of the point x minus h, x plus h, and as h goes to 0, so you are looking at intervals containing x of arbitrarily small size. Therefore, Vitali coverings will come very naturally when you want to study differentiation or other local properties. So now in all that we follows, mu star equals natural outer measure occurring in the construction of the Lebesgue measure. So you take the intervals and then you take sigma mu of ik union ik covering E, and then the infimum of all these sums is called the mu star. Okay, so this definition we know already. So now we have this important technical lemma. It's called the Vitali covering lemma. Let E contained in R, mu star of E finite. Let I be a Vitali covering of E. Then, given epsilon positive, we can find a finite subcollection of I say I1 to In such of disjoint intervals such that mu star of E minus union j equals 1 to n ij is less than epsilon. So you are having a Vitali covering of a set of finite outer measure, then you can extract a disjoint collection of intervals such that their union covers almost completely the given set, namely almost covers it means given any epsilon it will cover E except for a set of measure less than epsilon. Okay, so this is the Vitali covering lemma, and so proof. Observe that the intervals can be open, closed, or half open. By adding or removing endpoints, measure does not change. So nothing changes as far as the measure is concerned, and therefore without loss of generality we assume all intervals in I are closed. Now mu star of E is finite, implies there exists U open, U containing E, and mu star of U, which is also equal to M1 of U, is also finite. In fact, can be as close to E mu star of E as you like, but that is not something which we are interested in. Further, since we are dealing with a Vitali covering, that means only small intervals count. Okay, without loss of generality, for every I in I, we have I is contained in U. Okay, so we have this set U, and so we only take intervals which are contained in U also. Okay, so these are all the initial without loss of generality simplifications. Okay, now let us choose I1 in I arbitrarily. Having chosen I1 to IN disjoint, we choose IN plus 1 inductively as follows. If E is contained in union I k equals 1 to n I k, process stops. So we have already got I1 to Ik, which are disjoint, and they cover completely E. So E minus that is empty set, and therefore measure 0, so less than epsilon, so you don't have to worry at all. So secondly, if not, let X belong to E minus union k equals 1 to n Ik. Now this is closed, so X is not there, so the distance d equals distance of X from union I equals 1 to n Ik, k equals 1 to n Ik is positive. So since I is a Vitali covering, there exists I in I such that X belongs to I and M1 of I is as small as I like. I am going to say delta by 2, d by 2. So by and of course, and so I intersection Ik is empty for all 1 less than equal to k less than equal to n. Because this measure itself with d by 2, it contains X, and X is at least d from each one of these sets, and therefore I cannot intersect that set. Okay, so now so what have we established? So thus, given point in the complement, you can always, there exist intervals which do not intersect I1 to Ik. So now set So the conclusion, that is, given uh, uh, there exists I in I disjoint from I1 to Ik. And X belong to I. Okay. So now you set Kn to be the supremum of M1 of I belonging to I intersection Ik is empty, 1 less than equal to K less than equal to N. So, by assumption, all intervals in I are contained in U. So this implies that Kn is less than equal to M1 of U, which is finite. So Kn is a finite quantity. We have taken a supremum over something, so we want to know that it is finite. Now find In plus 1 such that In plus 1 intersection Ik is empty, 1 less than equal to K less than equal to N, and M1 of In plus 1 should be less than or equal to, of course, Kn, because that is the supremum, and I want it to be greater than half Kn, because the definition of the supremum is that. So I have just used the definition of the supremum. Okay. So if this process does not terminate at any finite stage, so what do you mean by terminate at a finite stage? That means the union covers E, therefore you are through, because that is the first step. Okay, so now we have that it does not convert any finite, so there exists a infinite sequence of disjoint intervals Ik, K equals 1 to infinity in I, and this implies that union of Ik, K equals 1 to infinity, is also contained in U, and therefore that implies sigma M1 of Ik is convergent. So given epsilon positive, choose capital N in capital N such that sigma K equals N plus 1 to infinity M1 of Ik is finite. Because it's a convergent series, the tail can be made as small as you please, not finite, sorry, as small as you please, and therefore you have less than, say, epsilon by 5, and set R to be E minus union K equals 1 to N Ik. So these are disjoint intervals, they are contained in I, and then so we are through. So claim M1 mu star of R, sorry, is less than epsilon, which will complete the proof. So let x belong to R. So there exists I in I intersection ik is empty 1 less than equal to k less than equal to capital N. Okay. Assume, if possible, I intersection ik is empty for all k. We will get a contradiction, so this will not be possible. Why is this so? Then this will imply that 0 is less than m1 of I, because that's an interval, okay, and that's less than equal to kn, which is less than equal to m1 of in. But kn is given here, and m1 of in plus 1 is kn is less than 2 times m1 of in plus 1. 2 times m1 of in plus 1, and that goes to 0, and therefore you have a contradiction. Okay, so there exists n which is greater than capital N, such that I intersection in is empty and non-empty, and I intersection ik is empty for all 1 less than equal to k, strictly less than n. So this is the first one which we are going to take. Now m1 of I is less than equal to k n minus 1, because it is disjoint from up to n minus 1, it's disjoint. So the supremum of all those such sets is kn minus 1. So you have this, and that is less than equal to 2 times m1 of in by choice, which we already mentioned before here. So let Cn be the midpoint of in. So x belongs to I, and x of course x belongs to I, that is x belongs to I, and I intersection in is not empty. Therefore, mod x minus Cn is less than or equal to the length of I, that's the maximum possible, plus half the length of in. But m1 of I is 2 times less than this thing, so this is less than equal to 5 by 2 times m1 of in. Now you said Jn is the interval Cn minus 5 by 2 m1 of in, Cn plus 5 by 2 m1 of in. Then x belongs to Jn, and m1 of Jn is less than or equal to 5 by 2 m1 of in, twice that, so that is 5 times m1 of in. So, and n is greater than or equal to capital N. So for every x in R, there is a n bigger than n such that this is true. Okay, so this implies that R is contained in union Jn n equals capital N plus 1 to infinity. So mu star of R is less than or equal to sigma n equals n plus 1 infinity m1 of jn, and that is less than or equal to 5 times sigma k equals 1 to n plus 1 to infinity m1 of ik, and that we know is less than epsilon by choice. That's how we choose here. So mu star of R is less than epsilon, and that completes the proof. Okay, so this is a fairly complicated lemma, but anyway, there are no deep ideas in it. It's just a question of selecting definition of supremum, summation of series, and so on. But it's there are several. So remark, in the literature there are several similar results all called Vitali covering lemma. And in all space dimensions. Not necessarily R, you can have an R2, R3, Rn and so on. And the basic idea is what? That if you have a set of finite outer measure which is covered by means of basic open sets which are of arbitrarily small size, then you can extract a disjoint finite set from them, such that the union almost covers E, in the sense that the uncovered portion can be as small of measure as we please. So that is called the Vitali covering lemma. Now we will use this to show that monotonic functions are differentiable almost everywhere. So that will be the next thing we will do.